artificial intelligence looks enormous. Millions of users, billions of interactions, autonomous agents, robotics, cloud platforms, entire industries beginning to reorganize around machine intelligence. But underneath all of that complexity is something surprisingly small: a semiconductor, a tiny piece of silicon capable of performing billions of calculations. And this creates one of the strangest realities of the AI economy. The larger artificial intelligence becomes, the more important this tiny component becomes, because every AI model needs computation. Every computation requires processors, and the most advanced processors require one of the most sophisticated industrial systems ever created. This means the future of artificial intelligence may depend on a bottleneck most people will never see. Not the model, not the application, not even the data. The chip.
The connection is simple, but its consequences are enormous. A chip creates computational capacity. Computational capacity allows a server to operate. Thousands of servers create a data center. Data centers create large-scale compute. Compute allows AI models to train and operate, and those models become products, platforms, businesses, and autonomous systems. The entire architecture is layered, and every layer depends on the one below it. This is why compute has become strategic. If intelligence is the new software layer of the economy, compute is the industrial machinery underneath it. More compute can mean larger models, faster training, more complex simulations, more capable AI agents, more autonomous systems, and more economic output. The race for artificial intelligence is therefore also a race for computational capacity, and computational capacity begins with silicon.
Imagine that tomorrow, every major technology company receives unlimited capital. Imagine governments provide incentives. Imagine thousands of engineers begin working on artificial intelligence. Imagine businesses around the world decide to automate. There is still a problem. You cannot manufacture advanced processors at the speed you can write software. A new AI application can be created in weeks. A new software feature can be deployed in hours. But advanced semiconductor capacity requires an industrial ecosystem built over decades. Factories, specialized equipment, materials, clean rooms, engineering talent, testing, packaging, energy, and precision on a microscopic scale. The AI economy can accelerate digitally. The physical infrastructure underneath it cannot. And that gap is where the bottleneck begins.
The simplest way to understand AI is to follow the dependency chain: AI model, compute, accelerators, semiconductors, manufacturing, equipment, materials, energy, capital. Each layer depends on another, and the deeper we go, the fewer organizations are capable of operating at the frontier. This is what makes semiconductors different from ordinary components. The final chip may be small, but the architecture required to produce it is enormous. A modern AI processor is not merely a piece of electronics. It is the final output of an industrial system involving thousands of specialized processes. That system is difficult to reproduce, and that difficulty creates economic power.
Here is the part most people never see. Designing a chip and manufacturing a chip are not the same thing. One side of the industry creates architectures,
The other turns those architectures into physical silicon. And manufacturing advanced chips is extraordinarily difficult. A modern processor contains billions of microscopic structures. They must be created with extraordinary precision, layer after layer, pattern after pattern, at a scale almost impossible to imagine. A mistake measured in microscopic dimensions can destroy an entire production cycle. This is why the semiconductor industry is not simply a collection of electronics companies. It is a specialized ecosystem. Designers, foundries, equipment manufacturers, material suppliers, software companies, packaging specialists, testing companies, and logistics networks. Each performs a different function, and each creates a potential bottleneck. And then the architecture goes one level deeper. The chip itself requires machines, extremely sophisticated machines, machines capable of manipulating matter at extraordinary scales, machines that can project patterns onto silicon, machines that allow engineers to build structures so small that they become difficult to comprehend. This creates a fascinating hierarchy. The AI chip depends on a factory. The factory depends on specialized equipment. The equipment depends on an even deeper supply chain. And the supply chain depends on decades of accumulated technological knowledge. The visible product is a processor, but underneath the processor is an industrial civilization of precision. This is the hidden architecture behind computational power. And once you understand it, the semiconductor industry starts to look less like consumer electronics and more like strategic infrastructure.
So why not simply build more factories? Because advanced semiconductor manufacturing is not like opening another warehouse. It requires enormous capital, highly specialized equipment, highly trained engineers, reliable electricity, ultra-pure materials, sophisticated software, complex supply chains, and years of accumulated knowledge. Even if a company has the money, money alone does not instantly create capability. This is what creates a powerful economic moat. The barrier is not simply financial, it is technological, operational, industrial, and institutional. A new competitor cannot simply copy the building. It has to reproduce the ecosystem, and ecosystems take time. This is why semiconductor capacity can become strategically valuable long before the final chip reaches a data center. This is where economics becomes interesting. A system does not need to have only one supplier to have a bottleneck. It only needs a layer that is extremely difficult to replace. That layer can become strategic. Because when demand rises faster than capacity, the bottleneck determines how quickly the entire system can grow. AI can generate enormous demand. Cloud companies can order more servers. Businesses can deploy more AI. Investors can provide more capital. But none of those things matter if a critical component cannot scale at the same speed. The bottleneck becomes the gate, and the gate determines the flow. This is one of the oldest principles of economic power. Control the scarce resource, and you influence everything that depends on it. In the industrial age, those resources included oil, steel, shipping, and energy. In the intelligence economy, compute is becoming one of them. And this creates another layer: geography. The semiconductor industry is global. Design may happen in one region, manufacturing in another. Equipment may come from another, materials from another, packaging from another.
and the final processors may be deployed across the world. This creates a strange form of dependency. No single location needs to control the entire industry. It only needs to control a critical layer. The result is a global network of specialization. And specialization creates efficiency, but it can also create vulnerability. Because the more concentrated a critical capability becomes, the more important that capability becomes to everyone else. The semiconductor supply chain is therefore more than an industrial network. It is a map of technological power.
There is another reason the semiconductor industry matters to wealth: capital. The economics of advanced computing are extraordinarily capital-intensive. Factories require investment. Equipment requires investment. Research requires investment. Talent requires investment. And capacity must often be built before demand becomes certain. This creates a relationship between capital and technology. Capital creates capacity. Capacity enables innovation. Innovation creates new markets. New markets attract more capital. And the cycle continues. The companies positioned at critical layers can capture enormous economic value. Not necessarily because they sell the most visible product, but because the entire ecosystem depends on their capability. This is the architecture of infrastructure wealth. Own the system that others must use, and value can accumulate beneath the surface.
But hardware alone does not create an empire. The deeper moat can exist in software. A processor becomes far more valuable when developers know how to use it, when tools are optimized for it, when frameworks are built around it, when applications depend on it, and when switching becomes expensive. This creates another layer of lock-in. The hardware becomes infrastructure. The software becomes ecosystem. The ecosystem becomes dependency, and dependency becomes leverage. This is why the most powerful technology companies often operate across multiple layers. They do not simply sell a component. They build an environment around the component. Once developers, businesses, and infrastructure become embedded inside that environment, the product stops being merely a product. It becomes architecture.
Now the system begins to compound. More chips create more compute. More compute enables more capable AI. More capable AI creates more applications. More applications create more business demand. More demand attracts more capital. More capital funds more infrastructure. And more infrastructure creates demand for more chips. The system becomes a flywheel. This is why the semiconductor industry is increasingly connected to the broader AI economy. It is not simply supplying hardware. It is sitting at the beginning of a reinforcing economic cycle. The faster AI adoption grows, the more valuable computational capacity becomes. And the more valuable computational capacity becomes, the more strategically important its bottlenecks become.
And now we reach the larger implication. Compute is becoming strategic power because artificial intelligence is moving beyond chatbots into cybersecurity, research, robotics, manufacturing, finance, healthcare, logistics, energy, and autonomous systems. The more industries become dependent on AI, the more important computational capacity becomes. That changes the meaning of a semiconductor. It is no longer simply an electronic component. It becomes part of the infrastructure of national competitiveness. The countries and companies capable of accessing advanced compute gain a different kind of capability. They can train, simulate, optimize, automate, and accelerate. In an economy increasingly organized around intelligence, compute becomes a form of industrial capacity.
This gives us a different way to look at technology. Most people look at the product, the AI application, the chatbot, the robot, the autonomous agent, the cloud platform. But ASUTSEN looks underneath. What does the product depend on? What does that dependency depend on? Where is the bottleneck? Who controls it? And what happens when demand grows faster than supply? These questions reveal the architecture, and architecture reveals leverage. The AI revolution, therefore, has two economies, the visible economy and the infrastructure economy beneath it. The visible economy gets the attention. The infrastructure economy captures the dependency, and dependency can become leverage.
So the real story of AI is not simply about artificial intelligence. It is about physical intelligence infrastructure, a digital revolution built on physical machines, software built on silicon, algorithms built on compute, compute built on factories, factories built on equipment, equipment built on knowledge, and the entire system built on capital. That is the hidden architecture, and it tells us something important about the future. The winners of the AI economy will not necessarily be the companies with the most visible applications. Some of the greatest leverage may belong to the companies controlling the infrastructure everyone else needs. The bottlenecks, the platforms, the compute, the chips, the energy, the networks, the capital. Because when everyone wants to build the future, the companies providing the tools to build it can become the infrastructure of that future.
A chip may fit inside your hand, but behind it is an industrial system spanning continents. And that system is becoming the foundation of artificial intelligence. So the next time you see an AI model, do not only ask what the model can do, ask what allows it to exist. Ask where the compute comes from, ask who manufactures it, ask what machines make the chips, ask where the energy comes from, and ask who controls the bottlenecks. Because the future is rarely controlled at the surface, it is controlled underneath, where dependency becomes leverage, where infrastructure becomes power, and where capital follows the architecture.
Artificial intelligence may be the visible revolution, but silicon is part of the hidden machinery making that revolution possible. And this is only the beginning. Because once you have enough chips, you need somewhere to put them. You need data centers. You need enormous amounts of electricity. You need cooling. You need networks. You need capital. And you need an infrastructure capable of supporting an economy built around machine intelligence. The chip is only the bottleneck we can see. The next bottleneck is much larger. ASUTSEN. Architecting wealth. Automating future.
The AI revolution needs chips, but chips need somewhere to run, and that place may consume more power than most people realize. Next, the data centers behind AI.